Section 11.10 Block chaining. Block chaining is a valuable tool that strengthens any block cipher. Block chaining means using each block to help encipher the next block. In effect, chaining is a ripple cipher operating on blocks rather than on individual characters. The group of bytes carried forward from block n to block n+1 is called the chain vector. Since the first block in a message does not have a predecessor, most chaining schemes use an initialization vector, IV, for enciphering the first block, as though it were the chain vector from some imaginary predecessor block. The initialization vector can be derived from the encryption key, or may be treated as an additional key for the encipherment. Aside. The block chaining used for Bitcoin and other cryptocurrencies is a specialized form of the block chaining used in cryptography. Here is where they got the idea. The most common form of chaining is combining the chain vector with the next block, character by character. The most common method of combining characters is exclusive OR. However, any of the combining methods described in section 11.8 can be used. This is normally done in one of 4 modes. For the greatest strength, the chaining operation should be cumulative. First, the chain vector from block n-1 is combined with block n. This result becomes the new chain vector, which is combined with block n+1. Chaining mode PP is the strongest, and chaining mode PC is second best. Modes CP and CC are far weaker because Emily can see the chain vector. I recommend that modes CP and CC be used only with the combining functions XOR S, add S, and poly. Although modes CC and CP are weaker, there is an advantage to using them. In modes CC and CP, it is not necessary to have a separate initialization vector. Sandra can use the last block of the plaintext message as the initialization vector. Riva can simply decipher the last block first. In fact, Riva can decipher any block without needing to decipher the block before. This can be valuable if the cipher uses indicators, section 14.3. Riva would decipher the indicator block first. Let's look at some stronger ways of chaining blocks. Section 11.10.1 Polyalphabetic chaining. Exclusive OR is a weak method of combining block n with block n+1. A better way is XOR S, namely using exclusive OR first, then using a simple substitution on the resulting characters. Far better than that is to use poly, a general polyalphabetic cipher. Use each character in the chain vector as a key to select the row in the tableau for enciphering the corresponding character in block n+1. Any of the 4 chaining modes can be used. Mode PP is strongest. Section 11.10.2 Enciphered chaining. The standard modes for chaining use either the plaintext or the ciphertext of block n as the chain vector, as is, with no modification. It is far stronger to apply some encipherment to the chain vector. This can be rudimentary, such as a simple substitution or a piecewise reversal, section 4.6. Such simple methods can be effective if the substitution or transposition is different for each block. A key ripple is well suited for this purpose, section 11.8. The encipherment used for the chain vector should have its own independent key. If the chain vector is more strongly enciphered, modes CC and CP will no longer be weak. Section 11.10.3 Lagged chaining. Chaining is not restricted to the preceding block. Chaining may also utilize earlier blocks. Block n may be combined with block n-I, or with multiple previous blocks, say block n-I and block n-j. If I is greater than j, this requires an initialization vector of I blocks. Similarly, the chain vector can straddle several previous blocks. For example, the chain vector can come from the last half of block n-2 and the first half of block n-1. Section 11.10.4 Interior taps. One weakness of using either the plain text or the ciphertext as the chain vector is that these are, or may become, known to Emily. One solution is to encipher the chain vector, as in section 11.10.2. A second solution is to take the chain vector from some intermediate round of the block encipherment. This is called a tap. For example, if the block cipher has 10 rounds, you could use the output of the 5th round as the chain vector. Combine this chain vector with the plain text of the next block before starting to encipher the next block. This is mode IP. This can be taken a step further. You can use multiple taps, and they can be combined with the following block in multiple places, either with the plain text, with the ciphertext, or between rounds of the encipherment. Each tap produces a separate chain vector, so for n taps you must have n initialization vectors. Any or all of these chain vectors can be enciphered. The chain vectors can be enciphered using the same key, or each one can have its own independent key. A ripple cipher, section 11.8, is well suited for enciphering the chain vectors. Section 11.10.5 Key chaining. Normally, chaining is done on the text of each block. However, it is also possible to use chaining with the keys. Suppose that you have a block cipher where the same key, K, is used for every block. That cipher could be greatly strengthened by using a different key for each block. One way to accomplish this is by chaining. You encipher the first block using K as the key. An initialization vector is optional for key chaining. Then you can encipher the second block using K.P1, K.C1 or K.I1 for the key, where dot represents one of the combining functions, such as XOR S or add S, performed byte by byte. Likewise, you encipher the third block using K.P2, K.C2 or K.I2 for the key, and so forth. This gives you 3 new chaining modes, PK, CK and IK. It is possible to use both key chaining and block chaining at the same time, say PK with IP. This is an extremely powerful combination.